So vertical circles. There's going to be three main types of vertical circles. Ferris wheels, nice vertical circle. Roller coaster loops, which are similar to Ferris wheels, but with one, maybe two key differences. And spinning something in a vertical circle on the end of a string. First of all, let's look at a Ferris wheel. A person rides on a Ferris wheel. They sit on a Newton scale that measures normal force. Well, of course, scales measure normal force. At the bottom of the Ferris wheel, what does the scale read? Does the scale read mg? Does the scale read more than mg? Or does the scale read less than mg? You know what? We're going to vote. Again, how high you hold your hand up is how sure you are of the answer. I'm positive, pretty sure. I'm only guessing because Mr. Duo can make fun of me if I don't vote. So, you ready? At the bottom, who says this is easy, Mr. Duick? You read mg. The answer is A. 1, 2, 3, 4, 5. Oh, 5, 6, 7. I think I saw 8. Who says no? You're going to read more than mg. Who says no? You're going to read less than mg. 2, 3, 4, 5, 6. Kessler, what are you voting? Sorry? Kessler's going here? What did you vote?
I'll go for A.
For A? You know what this might be a good job for? A free body diagram. Let's draw a free body diagram at the bottom here. I'm not going to represent this with a dot. They gave me a picture. What are the forces acting on this person? Get the obvious one. Get the obvious one. Boy, a little worried there. You ready? What path is this person tracing out? A circle. Where must the winning net force be pointing? Toward the... What else? mg. What other force? Bigger, smaller, or the same size as mg? What path is this person tracing out? A circle. Where must the bigger force be pointing? Toward the... So I'm going to draw the normal force bigger or smaller or the same size as mg. Has to be. Kessler, what's the correct answer? Darn right. You feel heavier at the bottom of a Ferris wheel. You do. In fact, you feel heavy at the bottom and you feel light at the top. Why is it? Oh, where it says explain your answer using principles of physics here. Accelerating toward middle. So winner is toward middle. Now, how do I know we're accelerating toward the center, towards the middle? We're moving in a circle. You must be accelerating towards the center. That's the single most important thing that I said you wanted to keep in mind. If you're moving in a circle, you're accelerating towards the center. And so I wrote here in example 2, on a Ferris wheel, people feel heavy at the top, light at the top, and heavy at the bottom. Why? We've already done heavy at the bottom. Let's do light at the top. You know what this is a good job for? What are the forces acting on this person? Get the obvious one. What path is this person tracing out? A circle. Where is the bigger, larger winning force going to be pointing? Toward the... So, the normal force is smaller. And remember, the scale measures the normal force. What you think of as your weight is the normal force. You'll feel lighter at the top. You'll feel a smaller normal force than mg. I'm not going to do an explanation. I think the free body diagram covers it. In Latin, the word centripetal means towards the center. So the fancy word for circular acceleration, it's actually called centripetal acceleration. But if you say circular, I'll know what you mean. When I go AC, technically that C stands for centripetal acceleration. But if you just want to remember Deegan, circular, no one's going to know. It works. So when an object is moving in circular motion, it has an inwards centripetal acceleration. And by Newton's second law, there has to be an unbalanced force in the same direction of acceleration because F equals ma. So an object moving inwards has a centripetal net force. So I use the following notation. AC is inwards acceleration. FC is inwards net force. You can think FC as F circle. I'll be thinking centripetal force. Here's the key idea then. In our winner minus loser approach, the centripetal force, Fc, will always be the net force, F net. And in the same way in our free body diagrams, F net never showed up on the free body diagram, Fc will never show up on a free body diagram. Do you see an Fc on here anywhere? No. Do you see an Fc on here anywhere? No. Fc will not show up on your free body diagram. What will show up is all the vector sums that got you there. So in the previous example, the Ferris wheel is a rigid wheel. The top and bottom of the wheel will always have the same speed, and the circular motion is uniform. That's not always true for vertical circles. So this is going to be the one time when we're not going to look at uniform circular motion, when the speed will be changing. And a good example is if you have a pendulum on the end of a string. If you see me in this vertical circle, do you notice it goes a little slower at the top? And it speeds up on the way down, and it slows up at the top. This is a changing speed situation. We can deal with it, but we can only deal with it easily in two locations. When it's at the very top, right here, and when it's at the very bottom, right here. We won't deal with it when it's kind of sideways. We could, bleh, yucky. So I wrote here, consider, oh, by the way, the Ferris wheel, because it's a rigid wheel, you're always going the same speed everywhere because it's all one solid mass. Not if you're, say, attached to a rope, or not if you're in a roller coaster loop, because in a roller coaster loop, you're going to slow down as you're getting near the top and then speed up as you're coming back down again. Example 3 says, write force equations at the top and at the bottom. Okay. You know what this is a good job for? Let's do the top first. What are the forces acting on the top? Actually, let's fib a little bit. Let's do the bottom first for a reason. What are the forces acting at the bottom? Get the obvious one. Which way? What else? A rope? What do we call that? Is tension going to be bigger, smaller, or the same size as mg? What path are we tracing out? A circle. Where must the bigger force be pointing? Toward the... So for part B, who's winning? Who's losing? What's that going to equal? MAC. Which can either be modified into T minus mg equals mv squared over r, or T minus mg equals m4 pi squared r over t squared. And this is the unfortunate yucky equation where I'm a bad teacher, because that t is tension and that t is the period, how long to go around once, and I apologize. So, sorry. In my defense, I have mentioned that we've run out of letters of the English alphabet and really need more, but yeah. What about at the top? What are the forces acting on the top? Get the obvious one. What else? Is it sitting on a surface? Is there a normal force? That's a bad guess. Sorry, but that is. What else? Tension, which way? Who's winning? Who's winning? What? They both are. Okay? So my equation is going to be tension plus mg, winner plus winner equals MAC. My equation is going to be tension plus mg equals mv squared over r, or the other one. Now, I've showed you the problem. Do me a favor, just scribble that one out. The nice thing is that will almost never come up. almost always when you're looking at a vertical circle, you'll want the velocity, not the period. So we're going to ignore that. But for what it's worth, it is out there because I'm a bad teacher. So in a vertical circle, we can have tangent forces that speed up the object, usually gravity. The object can speed up and slow down, but the net force inwards is MAC, which will be mv squared over r, or m4 pi squared r over t squared, because F is still ma, and if a is v squared over r, or if a is 4 pi squared r over t squared, then ma is mv squared over r, or m4 pi squared r over t squared. Rachel, you can see though how tempting or how easy it is to forget to put the m in and think that that's a force, because you've written so much it must be a force. No, it's an acceleration. So don't forget F equals what? Ma. Let's do one with some numbers. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. There's going to be a roller coaster loop in your future. How could there not be? Roller coaster loops. Alicia, what's example 4 asking me to find? What's it really asking me to find? Which force is the force the seat exerts on the person? I've never had F seat show up in a free body. Which force are we talking about here? Normal force. Okay? Any thoughts on how I might want to start out? I think definitely free body diagram. So, one of the key difference, well, first of all, what are the forces acting on this person? Get the obvious one. Which way? Okay. What else? Normal force. Which way? Normal force points in the same direction that your head is pointing. So which way is the normal force at the top of the roller coaster? Yep, say it. The big difference between a roller coaster loop and a Ferris wheel, in a Ferris wheel, your head is always pointing up, and so the normal force will always be pointing up. The N vanished there. The normal force will always be pointing up. In a roller coaster, when you're at the top, the normal force is pointing down. So if you're looking for a hook, which way is your head pointing? That's the direction of the normal force. So here, we're going to have also Fn. What path are we tracing out? A circle. What direction is winning toward the? Who's winning? Both of them. Yeah. It's going to be this. Fn and plus mg, that equals mac. Now, Alicia, I have two versions, don't write this down, of AC. I have this one, and I have, oh, sorry, pi squared, not pi r squared. That one. Which one do I use? I read the question. If the question asks for or gives me V, this one. If the question asks for or gives me the period, this one. Which one am I going to use here? I think you already knew. Okay. So let's get the Fn by itself. Actually, you know what? This is our first time doing this. Let's go very, very slowly. So let's go Fn plus mg equals mv squared over r. Now, Alicia, let's get the Fn by itself. How would I get the Fn? How will I move the mg over? Yep. The normal force at the top is going to be mv squared over r minus mg. Do the m's cancel? No. No, and so this is why whenever you're talking about the normal force, the m doesn't cancel. This is why little kids can often handle rides better than grown-ups can. Or this is why you may find as you get older and heavier, yes, it happens, you may suddenly age out of some rides. A ride that you remember going on when you were like 16, no problem, you go on it 20 years later. I'm feeling sick. It's because the normal force is much bigger for you. Haven't aged out yet, but we'll find out. Every year, it's getting closer. So the normal force is going to be, I've scrolled down. Alicia, what was M? 65? 70? What was V? Don't forget the squared. R I got from the picture. Minus 70 times 9.8. What do you get? Do you get 189? By a fluke, it works out nice. Do they feel heavier or lighter? How could I convert this normal force into its equivalent mass in kilograms? Sorry? Times 9.8? Which one? Divide. Okay. So although this person's mass is 70, what do they feel their mass is? They're going to feel like they're about to fall out of their seat because they're feeling much lighter than they're used to. They're not. There's still plenty of force holding them in place, but they'll scream with terror and glee. This will be a good roller coaster because they'll feel like they're about to fall out because they feel so much lighter. Ooh. What would happen in the previous example to the normal force if the roller coaster moved slower or if the roller coaster moved faster? You know what? Let's do that. We'll answer both. We'll do slower on the left. Alicia, did we get the normal force by itself in the previous example? Can you read me that equation, the one without numbers, the one that says Fn equals? Okay. Folks, as this number here gets smaller, what would happen to this answer? I'm not even, just even more generic. Bigger, smaller, or stays the same? Smaller. So as you go slower at the top, you'll feel even lighter. Okay? As V decreases, Fn decreases. Spencer was cleverly going, is there a squared? Is there a 4 times? It's not perfect that mg doesn't make it exactly a squared. There's no squared on the mg, so we can't use our twice as fast, twice the force here. What about if we go faster? And I would accept that here's your first true algebraic proof for using principles of physics right to explain. You could make up numbers and I would totally take that. So in other words, you could say, what was the velocity in the previous question as a number exactly? What was the speed? Try 9, try 11, and notice what happened. But here, I think we can argue, you know what? As V increases, normal force increases. You'll feel heavier the faster you go. What would happen if we slowed down so much that mv squared over r was less than mg? Yeah. The coaster, if it was the coaster, it would come crashing off unless it was locked to the track. You wouldn't make it through. That's a good thought. So, example 6. If the pendulum of example 3 or the upside down roller coaster of example 5 are moving at minimum safe speed, underline minimum safe speed, what would that imply about the forces? Minimum safe speed, as slow as you can possibly go, you're feeling as light as you possibly can. What's the lightest you could feel exactly as a number? Okay, minimum safe speed, you can write just underneath it. What that really means is the normal force equals 0. Let's do the roller coaster, since we just did the roller coaster. Let's do that first. So we would have this. What are the forces acting on this? Get the obvious one. Gravity and normal force, both pointing down. We would say normal force plus mg equals mv squared over r. But if we're at the minimum safe speed, Deegan, what's the normal force exactly as a number? If we're at the minimum safe speed, what's the normal force exactly as a number? Oh, now do the m's cancel? Yep. In fact, just for giggles, let's get the v by itself. What is the minimum safe speed for a roller coaster loop at the top? It looks like it's the square root of GR. And I always make that joke because this is going to be kind of a built-in error check. If you're ever dealing with vertical circles and you are asked to find a speed and you do end up with the square root of GR, even if there's other stuff inside the square root, you've probably done it right. Now, for the pendulum, was there a normal force? Is it sitting on a surface? So watch closely. I'm going to slow down, slow down, slow down. What force is 0 at minimum speed? Can you see the rope became slack? So, tension is 0. So where we wrote a little Fn equals 0, let's put in front of it or behind it T equals 0 or normal force equals 0, depending on which one of those two situations you're looking at. What are the forces acting at the top? Get the obvious one. We have gravity down. We have tension down. In fact, we have tension and gravity equals mv squared over r. But if we slow down to minimum possible speed, how big is tension exactly as a number? Oh! In fact, don't I get the same equation for v? Well, that's kind of cool. It turns out the physics of these two phenomena very similar. Very similar. How many of you as a child, or maybe as a teenager, have ever taken a bucket of water and spun it vertically and wondered at, oh, the water doesn't spill? You all done that? Okay, it's a hot sunny day. How many of you have taken it one step further and asked, how slow can I go and still stay dry? Because that's kind of a win, because if you get wet on a hot summer day, that's a win anyways, right? So example 7 says this: if we spin a bucket of water fast enough, it's possible to momentarily invert the bucket but not have any water fall out. Why? Annika's she's having good memories there. Yeah. I'm hoping that that's something that all of you have tried. And if you haven't, that's your homework this summer. Okay? Big bucket, small bucket, doesn't matter. Why? What might this be a good job for? Let's draw a free body diagram on the water. What are the forces acting on the water? Get the obvious one. What else? I think we'll call it a normal force. Fn and Fg. Usually I write mg. I don't know why I wrote Fg this time, but yeah, which is going to be mg in my next line. As long as there is a normal force, in other words, as long as the water feels like it has weight, it won't come pouring out. Because we just said the minimum safe speed is when the normal force is 0. We said if the normal force is negative, if the speed is so slow that mg is larger, they'll fall. So that tipping point is right when Fn is 0. So let's write an equation. What path are we tracing out? Which way is the winning direction? Toward the? Who's winning? They both are. What's the minimum safe speed when the normal force equals exactly what? So I'll write at minimum safe, instead of speed, v, Fn equals 0. So, as long as we have an Fn, we're okay. Yes? Let's get the Fn by itself. No, that's at minimum safe speed. Let's get the Fn by itself in this equation. How can I guarantee that I'll have a normal force bigger than 0? I think as long as this number is bigger than that number. I'll stay dry. As long as mv squared over r is greater than mg, oh, the m's cancel, as long as v squared over r is bigger than 9.8, we stay dry. And that's the experiment that you were actually doing when you were trying to see as a kid, how slow can I go? How slow can I go? Okay. Is that all right? Example 8. I like example 8. I like example 8. Example 8 is a nice question. A student is in a car that is traveling at 28 meters per second on a hill of radius 120 meters. When the car is at the top of the hill, what's this question asking me to find? I think normal force. What upward force does the seat exert? Gotta be the normal force. Okay. Any suggestions on how I might want to start out? What are the forces acting on this car? Get the obvious one. What else? Which way? Bigger, smaller, or the same size as mg, and convince me. Why? What path are we tracing out? A circle. Where must the winning bigger force be pointing? Toward the, okay? By the way, do you notice again, has FC showed up on my free body diagram? No! The same way Fnet never showed up on my free body diagram. This is the left-hand side of the equation. And now I say, who's winning? Who's losing? What's that going to equal? MA, but we're moving in a circle, MAC. What am I trying to find? Oh, swappy dance. Yes? What's right in front of the normal force that I don't like? The minus sign. So I'm going to plus this here, minus that there, and I'll get mg minus MAC, and if you don't mind, I'll put the normal force on the left because that's kind of where we're used to seeing things. Which A, yeah?
Why in this example FN is faster and the example, like, there was another example when FN was the same direction?
Like this?
Yeah.
Your normal force, the seat, always pushes in the same direction that your head is pointing. So here at the top, which way is your head pointing? Down. The seat's pushing you down. Here, which way is your head pointing? Up. The seat's pushing you up. In the Ferris wheel, it's a good question. Which way is your head pointing? Seat's pushing you this way. Here, the seat's pushing you this way. Seat's pushing you this way, pushing you that way, pushing you that way. So the seat, the normal force, if it's a person sitting in a chair, will always point in the direction that their head is pointing. Is that okay? So, I have two versions of A. Which one am I going to use here? The one with the V or the one with the T? How do I know? Okay, so this is going to become normal force equals mg minus mv squared over r. I've scrolled down. What was m? 72? What was g? 9.8. Minus 72. What was v? Sorry? 28. Don't forget the squared. And what was r? 120? Okay, what do you get? 72 times 9.8 minus 72 times 28 squared divided by 120. 120, Mr. Duick. Do you get 235.2? No, yes? Question?
It's m like m times v squared over r, or is the m also equal to r?
They both are, but you only do it once. 5 times 6 divided by 3. You don't go 5 divided by 3 times 6 divided by 3.
Well, no, it just looked like in some of them it looked like you were just not dividing the m by r at all, just having it separate there. But sometimes. Well, no, like,
That is the same thing as that. Makes no mathematical difference. Because that's over 1, technically. And then how do you multiply fractions? That's the easiest. It's top times top, bottom times bottom. So you'll end up with mv squared over 1 times r, or just plain old r. There you go. Good question. Divide by 9.8. How many kilograms do they feel right now? Do they feel heavier? Do they feel lighter? Okay. That's why you may have found, I know I grew up in Abbotsford. There's a specific hill that all of us know about. It's on North Parallel Road, just near Whatcom. If you take that hill at the speed limit, you get that stomachy feeling. I don't know if there's one around here, but kids, when you get your driver's license, go over that hill. Oh, that's pretty cool. Okay. Oh. How fast would the car need to travel for the student to feel weightless? I guess Fn would be 0. It would be the same free body diagram. Yes? In fact, it would be the same equation. mg minus Fn equals mac. But to feel weightless, no normal force. So it would become mg equals mv squared over r. What? We get our friend the square root of GR again? I probably did this right. So it's going to be the square root of 9.8 times 120. Okay. You get 34.3. Ooh. What if you went faster than the answer from part B? Yeah. Yep. You get error. Yep. Does that make sense? Okay. And again, some of this you might understand intuitively if you're doing the driving, but here's the physics of why. Sure. Go faster than the normal force of 0, something's got to happen. Example 9. Raj has a mass of 72 kilograms. He's riding a Ferris wheel. Oh, I like example 9. I like example 9. He's riding a Ferris wheel of radius 12 meters and is moving with a constant speed. At the top of the Ferris wheel, the bench that he is sitting on applies a normal force of 450 newtons. Huh. Rachel, what does A want me to find? Any suggestions on how I might want to start? I think so. What are the forces acting on this person? Get the obvious one. Yep. Which way? Toward the center? Good. Francesca, there's also a normal force. Which way am I going to point the normal force? Which way is this person's head pointing? Normal force is going to be pointing. Bigger, smaller, or the same size as mg, and how do I know? Why? What path is this person tracing out? A circle. Where must the winning force be pointing? Toward the... Okay. Rachel, give me an equation. Who's winning? Keep going. What are they asking me to find? I'm going to be brave and go straight to mv squared over r because they asked me to find v. Okay. Could have asked me to find the period, and that would just be how long does it take the Ferris wheel to go around once? That would be m4 pi squared r over t squared. I think there's one like that either in the lesson or in the homework. What are we trying to find? This is about my limit. I could get the v by itself. It would be times everything by r in brackets, divide everything by m, and square root. No. This is where I say, I'm going to just turn this into a number. What's m? G? Normal force, they told me. That equals mv squared over r. I'm going to crunch the left side and just turn it into a number. 72 times 9.8 minus 450. 255.6. Will I round off? No. I'll use, if it's a yucky number, I'll use my answer button. This isn't bad at all. I get, is it 255.6? That equals mv squared over r. Now, Rachel, I can get the v by itself. How will I move the m over? The m? Think so. How about the r? And then how do I get rid of the squared? I'll get v equals 255.6 times r divided by m square root. Oh, let's be bold and go to our calculators right now. So it's going to be answer button times r. What was r? 12 divided by 72, square root of that. And I get 6.53 meters per second. B. Oh, let me pause for a second. B. What does B want me to find? Okay. Darn right, a free body diagram. What are the forces acting at the bottom? Get the obvious one. What else? Bigger, smaller, or the same size as mg? And how do I know? Bigger normal force, yes? I should probably really exaggerate that so it stands out. There. What's my equation? What am I trying to get by itself? There. I didn't feel like rewriting it. It's going to be m, 72, v, I'm going to write 6.53 squared, but you know I'm using my answer button, right? All over, what was r? 12? Plus 72 times 9.8. 72 times answer button squared divided by 12 plus 72 times 9.8. And I get 961.2. Newtons. Sorry? I don't know. Let's see. Divide by 9.8. Oh, divide by 9.8. You feel like you have a mass of 98 kilograms. Ferris wheels, scary rides or tame rides? Yeah, I'm bumping up the numbers here to get some interesting results. I've been on a couple of Ferris wheels that go fairly fast, but not many of them do. Most of them, they're designed for you to see the sights. By the way, if you want to take a nerd trivia path, look at the very first Ferris wheel, built by, yes, George Ferris. They're named after him. It was massive, huge. It was, until about 20 years ago, the largest one ever built. And it was built in 1880 for the Chicago World's Fair. I would normally go on a tangent, but I got somebody to come and working the computer. And we have a thought puzzle. It says this. Can a child on a swing ever swing fast enough to complete? How many of you tried on your swing when you were a kid? Can you get over? You've tried this. So here's the question. Can you? You can't and you can. It depends, as always. With a standard swing that has chain or rope attached to the seat, you cannot. But if you have a solid pole attached to the seat, what we call a Russian swing, you can get this. How is he gaining energy? Is he going higher? Is his potential energy increasing? Doesn't that violate the law of conservation of energy? Where's it coming from? Yeah, this is what you do in a swing. Swing is good exercise. Yeah, by shifting your weight and pushing at the right time, you're transferring energy from your body into the swing apparatus. This has got to be a pretty good workout too, because you're getting a lot of energy here. So, can you do a vertical swing with solid poles? Yes. But otherwise, the answer is no. How many of you have seen at skate parks, they have like a pipe and you can do a skate, if you're really fast? Could you run that? What's your homework? Number 1. Number 2. You can skip number 3. Haha. 4 is good. 5 is good. 6 is good. 7 is good. Skip 8. It's cool, but I'm going to skip it. You can also skip 9, 10, and 11. Ha ha ha. 12 is good. Obviously, skip A. 13. 14. Oh, roller coaster loops. Got to do roller coaster loops. So are you seeing why I went on my big rant about directions in the last lesson? Which way are you accelerating? Towards the center. So in your free body diagram, who's winning? Towards the center.